Good morning, my chemistry students. This is my first virtual video for you all. I've been practicing a little bit with my HL biology students, but here goes the first try with chemistry for 10th graders. Just to catch you up on my overall mindset here, we wrapped up with Unit 2 on chemical bonds. We're going to skip Unit 3, which was chemical reactions. It's a good one to do in person, partially because it's got a lot of cool experiments, because we can actually see chemical reactions happening. So I'd love to be able to do that one with you as long as school opens back up at some point here. And additionally, there's a good amount of math. And I know a lot of people have math phobias. I'd much rather be there to support you one-on-one. If we end up doing it online, I'll have plenty of videos. It'll walk you through step by step. You just got to have enough grit to rewatch the video and try again and ask for another example, that kind of thing. All right, back to where we're at. We are now in Unit 4, which is a unit on matter. States matter, phase changes between types of matter, how pressure and temperature both affect matter, what happens to the energy and the temperature as matter goes through these phase changes. Our very first lesson is just types of matter, how to categorize matter into one of the 4 types. We're going to be able to say that matter in front of me is an element, is a compound, or a homogeneous mixture, or a heterogeneous mixture. I don't care if you say homogeneous or homogeneous. I don't care if you say heterogeneous or heterogeneous. Up to you. On your own, this is a really cool video, Cosmic Voyage. Go ahead and click that and see what that is all about. And also this video on what is matter and what is not matter. I will skip past those to actually creating this nice little flowchart for all of matter. If you do not have a printed version of this, which I imagine most people do not have an at-home printer, just go ahead and use a piece of paper, blank piece of paper, and go ahead and write this out. First, pause it, do that, then come on back. First, broadest category is matter. All right, matter is anything that has mass and volume. So what is not matter? Energy is not matter. Kinetic energy, potential energy, solar energy, thermal energy, all of those things are not matter because energy does not have mass and volume. But if it does have mass, meaning you can put it on a scale and it has something there, and it takes up space, volume, then poof, matter. The 2 broadest categories matter can be split into. We can go one way or the other, but we can't go both. One of them is pure substances. Pure substances, all particles are the same. All right, whatever group they have, all of the little groups of particles are exactly the same. What does that mean? Okay, well, makes sense to go with the easiest one first. Elements. If all the particles are the same, they all have the same exact type of atom. Only that one atom. All atoms have the same number of protons. Remember, that's what defines an element, same number of protons. So it could be the examples of all of them are hydrogen. Now, it could be hydrogen by itself, or it could be hydrogen paired with another hydrogen. Now, even though H2 has 2 atoms, they're both hydrogen. Same with O2, that kind of thing. Could be gold, AU, doesn't matter. But they're all found on the periodic table of elements. That would be a pure substance, furthermore an element. Next, if all the particles are still the same, except we have chemical bonds between atoms in those particles, and those atoms are different elements, this gives us compounds. Different elements, but all the same molecular formula. Example being H2O. All right, you have an oxygen single bonded to a hydrogen. That's the particle. Your particle is the water molecule. So here is the particle. Now there are billions and billions of those water molecules. But every single one of those particles, every single one of those water molecules consists of the same elements in the same ratio, sharing the exact same orientation of bonds. All right. So, pure substances, all the same atom, or hey, different compounds, hey, different atoms, but all locked together in the exact same molecular formula, such as H2O. Now, if all the particles are not the same, then that's this other division here on the right-hand side. This matter would be considered mixtures. Different particles. Same space. So they are mixed up, hence the word mixture. You have different particles sharing the same container, the same space in the air around us, and they're not chemically bound together. They are separate particles. These waters are separate particles, but each of them are the same composition. In this case over here, instead of just water, there might be something else in that water. Let's subdivide these mixtures into two types. The first type is homogeneous. Homogeneous. It's, I believe, properly said homogeneous, but I and most people can spell it better if they sound it out and say homogeneous. Up to you. So homogeneous mixtures. Yes, these mixtures have different particles. Yes, they're sharing the same space, but the homo, meaning same, it is the same composition, or same composition, meaning percent throughout. Right? It is mixed so well because it's evenly distributed throughout the mixture. You can't actually see the separate compounds. Can't see the different particles. If you remember back to biology, this is the word solutions. Use solutions for homogeneous mixtures. For example, we might have salt water. All right, so we have, let's say, 90% H2O, but we also have 10% NaCl. All right, so we've got our water compound, but we also are going to have some Na. That won't get complicated. I'm just going to say NaCl. We'll have more water molecules and more NaCl. So we've got this molecule. Now the real story for this is a little more complicated. It will break down, but for simplicity's sake, let's just imagine NaCl is a single molecule staying together, and we've got this molecule, your water. So we've got these orange molecules and the green molecules. Two different particles sharing the same space, but you can't see the salt apart from the water. It's mixed so well. Last one is heterogeneous mixture. Heterogeneous mixture. The hetero meaning different. It's different composition. Throughout. You can see the different particles. And you can see them because they're not evenly distributed. They're not the same composition throughout. So good examples of heterogeneous mixtures, if we carry along our analogy, is sandy, salt, water. Sandy salt water, for a second, if you capture it right at the breaking wave, it may look like the sand is evenly distributed in whatever container you caught your sandy salt water in, right? It may look like it's just this nice, even distribution of sandy salt water. But give it a moment, give it a minute, give it a couple minutes, and you will start to see the sand settle to the bottom. As that sand settles to the bottom, you're seeing it's clearly heterogeneous. That sand is not evenly distributed through the salt water. You still have H2O and NaCl up here evenly distributed, but the sand is not. The sand is what makes sandy salt water a heterogeneous mixture because it is not evenly distributed. It falls out of solution. All right, quick overview from the top. Matter has mass and volume. If every particle is exactly the same, it's a pure substance. If all those particles are composed of the exact same element, same atom with same number of protons, then that's an element. If those pure substances have the same molecular formula, such as H2O, then it's a compound. But they're the same compound, same formula, so still same particle. If, however, that matter, which has mass and volume, consists of different particles occupying the same space, different particles meaning not chemically bound to each other, then it is either a homogeneous mixture. Those different particles in the same space are so well mixed that we can't see the difference between the particles, such as salt water. You cannot see the salt apart from the water. Or that mixture with different particles in the same space has a different composition throughout, such as sandy salt water. At the start, it may have looked homogeneous, but the sand falls out, so the sand is not evenly distributed throughout the container. It falls to the bottom, making sandy salt water a heterogeneous mixture. Last, let's get a little practice. This tree. What do I see in this tree? Well, in this tree, I can see leaves. Even within those leaves, I can see veins. I can see different parts of that. I can see wood, which is composed of many different molecules along these branches. I can see knots. I could see roots that look different and distinct. If you can see all of that stuff, then they must not be evenly distributed, right? So this tree, complex organisms are heterogeneous mixtures. You, your dog, your cat, all organisms are heterogeneous mixtures. They're very easy to tell the difference between the molecules in them. Pure gold. Pure gold is found on the periodic table. So pure gold is an element. I don't have my periodic table in front of me. Super handy. 79 protons. On the periodic table. Gold, 79 protons. So all the same element. All the same atom. Pure water. Pure water. You already saw that one up above, so hopefully this is a quick, easy giveaway. Pure water is H2O. Would be a compound. Now, although that was a giveaway, our last one, tap water, is a little confusing. That's why I still gave pure water as my example. Tap water is not pure. Tap water also contains, depending on the municipality you live in, it contains metal ions. It contains chlorine to make it healthy to drink, safe to drink. It may be fluorinated, containing sodium fluoride for dental health. And, of course, H2O. So if it's H2O, yet also has metal and also has chlorine and also has fluorine in it, but we can't see the metal, we can't see the chlorine, we can't see the fluorine compounds, then tap water is a great example of a homogeneous mixture. All right. This may be a better, more helpful way for you to figure things out. You can use a dichotomous key, meaning you've got a choice to make. If you know what's matter, is the composition variable, meaning are there different things in it? If yes, it's a mixture. If no, it's pure. Can you separate that pure substance into simpler substances? If no, it's an element. You may have 1 billion gold molecules, but as you try to separate atom from atom from atom from atom, every single one of them is still gold. Another way is compounds. If you can separate the molecules of the atoms of hydrogen from the atoms of oxygen, then that is more simple. So that would be a compound. If you answered yes to composition is variable, is it uniform throughout? If it's not uniform throughout, it's heterogeneous. You can see the sand at the bottom and the water and salt up top. If it is even throughout, it is homogeneous. You cannot see the compounds that make up the tea separate from the compounds that make up the water. That is all I have for you today. Consult the plan. I've got 2 options for you. You can make your own Quizlet or flashcards for elements, compounds, homogeneous mixtures, and heterogeneous mixtures. Or you can take a Google quiz, but you're doing something to practice with this material. Nothing is graded while we're out of school, but I'd love to see that you're engaging and practicing, because we will not have time to relearn this, even if school goes back in session in 2 weeks. All right, good luck, everyone. It was fun learning with you.